Okay, we have here today a tricky integral sent to me by Sid. We've got the integral of x to the cos squared x times natural log x sinh 2x plus x to the sinh squared x cos squared x dx. Okay, now this one is kind of a puzzle, and the problem we have is it really looks like reverse product rule because we're adding two things. We've got some complicated expressions. The other thing is we've got a similarity here where like the derivative of cos squared x, this is actually sinh 2x. And then with the similarity between this and this, it seems like it has to be some kind of reverse product rule, but it turns out it doesn't quite work that way. I had to try this a few different ways, and the first thing I did was I tried to get the derivative of x sinh squared x. And the problem with that is it doesn't really work that well just because you don't get back an x cos squared x anywhere, so it didn't work for me doing it that way. But on my second try, what I did was I did a substitution for this right here. So I just set my u equal to x cos squared x. And for this here, we don't really want x in the base and in the exponent. So what we can do is actually change the base to e. We can write x as just equal to e ln x. So using that to rewrite this u value, I can write this as e ln x times cos squared x. And next we'll go ahead and we'll take our derivative. I'm going to need some more space because it's kind of a complicated derivative. Now what we're going to have first with the base e, we're going to get just back everything out. We're just going to get back the same thing. We're going to get back e ln x cos squared x. And then we need chain rule and all this, but then with that we're going to have product rule. So derivative of natural log x is going to be 1 over x cos squared x. And for the second part, we're going to have just natural log x. I mentioned before the derivative of cos squared x is going to be sinh 2x because first you use power rule, you get 2 cos x. Derivative of cos is sinh x, so you're going to get back this thing here. So we're going to write this as sinh 2x. Now what I can do to clean it up, first let's take this here and put it back and write it back this way. So we're going to write it as x cos squared x. And then what I'm going to do is distribute it in here to everything inside the parentheses. So we'll write this as like over x, then we'll have our cos squared x. Distributing it to the second part, we're going to have x cos squared x, and this is going to become ln x sinh 2x. But now with this x in the denominator right here, I can take this same base and divide it into this. We can write this as a minus 1 in the exponent here. And then for this thing, we can use an identity on this. So starting with this identity, if I just add a sinh squared on both sides, we can kind of bring it over here, and I'll subtract a 1 on both sides. So what we're going to have is cos squared x minus 1 is just equal to sinh squared x. And so let's just update this exponent here to sinh squared x. And now at this point, the thing to notice is what we have right here, x sinh squared x cos squared x. That's this second part right here. And then over here, x cos squared x ln x sinh 2x. This is exactly our first part right here. So what we can say is this whole thing, including the dx, this is all going to be just du. So what just happened is we can reduce our whole integral down to like just 1 du. Integrating this, we get just a u. All we need to do is just back substitute in order to finish it off. So for my final solution of this, we just get x cos squared x plus c, and that's it. So as you can see, I didn't really have a systematic way to do it. It's kind of just guess and check. So I don't really know a good method. Let me know if you've got a different way. But for me, it's kind of just looking at the complicated parts and trying different derivatives and seeing what works. Okay, there you have it. Thanks again to Sid for the problem. Thanks everyone for watching. Have a good day.